Figuring out IT issues. It's my distinct pleasure to welcome Shintaro Honjo from Mitsubishi Heavy Industries. So he's based out of the Houston office, and Mitsubishi Heavy Industries is actually quite significantly involved in CO2 capture, which makes it relevant to the discussions in this series. So in fact, they have designed and built the Patronal facility right outside of Houston, which I think is 5,000 tons a year as far as CO2 capture is concerned. So that's the classical amine-based capture system. So he'll talk a little bit about the technology that's involved in that. And we've recently started a collaboration with them. So for the second half of this discussion and the time that we'll have remaining, I'll give you some perspective on how the work at Mitsubishi is related to some of the more early stage development efforts here at Cornell. So to sort of establish a pipeline from lab to hopefully to deployment, give you some perspective on what's going on at Cornell in that area. So without further ado, okay, go ahead.
Okay, thanks. Thank you for the introduction. My name is Shintaro Honjo. I'm a general manager of the Global Research Innovation Houston office in MHI, Mitsubishi Heavy Industries America, based on Houston, and taking care of all the research and development activities of MHI technologies. So today, thank you for these opportunities. We are very pleased to present our technologies, and I'm going to talk about carbon capture technologies. We actually commercially deployed in Patronal project. It's south of Houston, and it's 5,000 tons per day of capture. And I'll give some summary and summary of technologies and the history of the R&D, and then also show there some current activities. Little bit about talk about the MHI organization. Brief introduction of MHI. Mitsubishi is a very long history companies, and lots of Mitsubishi Group companies, and it was different equity and different company, but Mitsubishi Heavy Industries is most oldest companies, and then starting from the shipbuilding companies. Currently, we are earning about $40 billion, and so almost outside of Japan, 54% sales, and then also operating income at 1.2 billion and 80,000 people employee in worldwide, and mostly in Japan, but we have lots of office and manufacturing factories in worldwide, and also doing the projects worldwide. We have lots of group companies, about 300. So we are doing these are business domains. We have 3 business domains: power and industry infrastructures, and aircraft defense and space. So a lot of areas we're covering that, providing the power plants, compressor pumps, turbine, and marine machinery, nuclear power plants, and also shipbuildings, forklift, machinery, transportation system, and also aircraft. Recently, we are going to launch the MRJ, Mitsubishi Regional Jet. Will be delivered in 2020. And defense system also located in Japan and taking care of the providing the defense system. Today, I'm going to talk about our CO2 capture system. It's belong in the environmental chemical plant engineering and divisions. And I show some background of the CO2 capture technologies. this is we call the Kansai Mitsubishi carbon dioxide removal process. We actually developed this process with collaborating with Kansai Electric company as a Japanese utility, and then we developed a proprietary solvent, amine-based solvent, and to apply this carbon capture system. We call the KS1 solvent. Very high CO2 capacity and low degradations and low regeneration energy. Lots of advance from the other, the monoethanol amine or type of conventional type of amine solvents. We do have the capability of the over 90% CO2 captures and the CO2 purity over 99.9+%. Okay. Maybe, yeah. Here's the 3 column here. So flue gas will be quenched and then brushed, scrubbed, and then remaining the SO2 or some impurities, and then quench out and then introduce the absorber, bottom absorber. Absorber and circulate in the solvent, amine solvent, and capture the CO2, and then emit it out clean gas top of the absorber. CO2 captured solvent will be recirculating and pumped up to regenerators. Bottom section of regenerator have the reboiler and introducing the steam to heat up the solvent and then dissolve the CO2. CO2 will be dissolved from the solvent and then compressed out and then provided the markets. So this is a basic amine solvent, conventional type solvent process. We have a lot of test facilities, and head of engineering office located in Yokohama, and we have several pilot facilities, including so first pilot was located 2 tons per day Nanko pilot plants located in the Nanko power station of Kansai Electric company. And this is a natural gas fired plants. And almost 1991, almost 30 years ago, we started the testing at the power stations. And we also developed that 1 tons per day Hiroshima pilot plants located in the MHI R&D centers using coal fire flue gas. They capture the CO2 and then testing for the impurity effect. And also we developed the 10 tons per day Matsushima pilot plant working with J-Power and located in the Matsushima. It's a Kyushu Islands in the west, just west of Japan Island. We have a big absorber test facilities. It was used to be used for the FZD, flue gas desulfurization technology development. And then we installed some packing for the CO2 capture technologies, and then testing the solvent distributors and then also flow patterns or distribution of the test CO2 capture absorber equipment. Okay, this is a global experience. So far we delivered 14 plants. It's a commercial plants, and firstly installed the Malaysia, that was used for the urea production from the natural gas fired natural gas furnace, and there's a lot of commercial plants about 200 to 500 metric tons per day of scale, and mainly for the urea or methanol productions from the natural gas, flue gas. And in the U.S., yeah, as I said, we developed the 4,776 metric tons per day for CO2 EOR projects from coal-fired boiler.
These megatons per day, that's the
Right.
production or what?
Oh, it's the CO2 capture.
CO2
capture,
capture,
right. It's not urea production. And so worldwide, and also few experience for the coal-fired boiler, but we had also testing purpose, and we developed the coal demonstration plants at the Plant Valley in Southern Company's Alabama Power.
Are you going to talk about how the CO2 might be used once it's captured? Is that?
So
I'd be interested whether any of it's being sequestered.
okay, these are all commercial plants.
Right, exactly.
So 100% of captured CO2 will
Is
be
used. Is utilized in products
Right.
of some type.
Urea,
Food products,
methanol, sometimes general use.
So it all makes its way back to the atmosphere in some sense, most likely.
Yeah.
Yeah. Right. Carbonated food.
Yeah.
Right.
Okay. Little bit about application of CO2. It's a summary of the CO2 usage. And yeah, probably can use the welding and dry ice or other use, but we mainly focus on the chemical usage for the CO2. Urea synthesis or methanol synthesis. Basically, both are coming from the natural gas, methane, but sometimes there is some excess amount of CO2 can be used for the enhanced productions.
I got it. Thank you.
So, and then also the last, I said that NRG project is CO2 EOR. CO2 captured, the CO2 will be injected in the oil field, the enhanced oil productions. So those are focusing area. And so a little bit about, talk about the process side of the methanol production. This is conventional methanol process, steam reformer and compression and synthesis of methanol and distillations. So we may use the CO2 recovery process to capture the CO2 from the flue gas from the reformer, and then return to the system to enhance the oil, enhance the methanol productions. Another application is urea productions. This is also a conventional process. Basically, they're using CO2 removal for the ammonia synthesis. But if we put the CO2 recovery process to recover the additional CO2 and mix with the recovered CO2, and so the ammonia can produce additional urea. Yeah, this is a summary of the urea production process. Okay, this is also a summary of the Plant Valley demonstration plants. It's a 25 megawatt equivalent, 500 tons per day CO2 capture at 90% captured, located in Alabama. We actually conducted the demonstration testing from 2011 to 14 over 12,000 hours. and then 250,000 tons were captured, and 125,000 tons were injected in the oil field. It's a storage field. It's not EOR purpose. It was a testing project for DOE funding.
Excuse me.
Right.
Before you were talking about 4 or 5 gigatons per day capture.
Metric tons.
Oh, metric tons.
Metric.
I'm sorry.
Yeah.
I see. I'm sorry.
Yeah.
Thank you.
Okay. So
Okay.
yeah, that's a brief summary of the test results, and I show some another results. We focus in the operation stability and then also load following, energy saving, and we also focusing on the aiming emission reductions. In case of the coal flue gas, including SO3 or another impurities, may have the cause of the aiming emission, additional emissions from the stock, and that creates another environmental issue.
Are these single method? Is this an MEA type system or a combination of other amines or some proprietary?
Yeah,
mix of
proprietary. Yeah,
proprietary mix
Yeah.
of amines. Okay.
right. We also tested with our MEA, but yeah, we compared with the test data.
see.
Yeah. Right.
This is very interesting.
When you see the load adjustment,
Yeah.
I couldn't see the number on
Oh, yeah, sure.
the axis here, but what kind of time scale are you talking about?
Okay. Well. Well.
I suppose the CO2 demand is like on daily or
Is it
month.
an hourly type time scale or daily? Or?
Well.
The x-axis is 30 hours.
Hours, 30 hours. Yeah.
How can you read that, Tobias?
Oh yeah.
Okay.
Okay. Excellent. I didn't remember. Yeah.
Supervisor.
Yeah. So this is the comparison of the manual operation and then control phase operations, and then keep the CO2 capture or CO2 output, whatever. And then we conducted such testing, and I also installed the amine reduction system, capture the amine emission. I mean that amine creates some aerosol together with SO3 or some acid fumes. And so we installed our capture system and then much reduced from the original emissions. Okay, so move on the Petronova project. We just completed, and from now operating from 2017 January, and we captured the CO2 from flue gas of the coal power plant, Urea Parish, and captured CO2 will be injected in the oil field, and then already NRGs and Hillcorp working for the oil productions. So here's a summary of the Patronal projects, and so CO2 will be transferred to the West Ranch oil field. Plant now own the NRG and JX oil. JX is Japanese oil companies. And captures 5,000 tons per day, and this 240 megawatts equivalent flue gas, and then 90% captures. And so we conducted the all EPC work together with TIC. And so HOMAS test was December 2016. This is the pictures, and this is absorber, and then this one is the quenchers. So flue gas come in here, and then scrub out, and then introduce this absorber. This this is a regenerator column. There's lots of cooling system and then compression system. Compressor, okay, here, and a cooling tower here. So, total summary of development of the CO2 capture plants. We started 1 tons per day of a pilot, and 10, 500, now 5,000 tons per day. So we conducted a bunch of the R&D activities to develop the one by one, and then we're now offering the over 10,000 tons per day commercial plants. A little bit about the Patronal CO2 overall system. In case of Patronal, we didn't touch anything about the coal-fired boiler, and other than the gas turbine, it was a cogeneration turbine system, and so we introduced the electricity from the gas turbine here, and then also the steam also was used from the combined system. So the CO2 just capture and then transfer to oil field. So basically, we have no interactions and no interruption of the boiler operations. Yeah.
So you capture it and you compress it and hydrate it and then put it, would you put it back in the boiler?
Yeah.
Back in the
Enhance the oil recovery.
From coal-fired power plant.
Yeah, so it's burning coal. to get
Burning
CO2
coal, yeah,
or
and
natural
it produce the
gas.
flue gas.
Oil,
CO2.
CO2 gonna stay.
Hopefully it stays, but they also get it out when they produce the oil, put it back in again.
Oh yeah, yeah.
Yeah.
In oil field, yeah,
It doesn't
they may have some CO2 recycle plants in case, yeah. But basically, capture CO2, inject in, and then produce the oil, and then some CO2 may be, yeah.
Question of how long, right?
Right.
How long does it stay there?
It's also depend on the oil wells, life of the oil well.
Exactly.
Yeah.
Right. And there's millions of holes drilled.
Right. Then last slide showing that effect of the flue gas composition. So basically, we are capturing the CO2 from the flue gas, but a variety of flue gas may cause that size of the CO2 scrubber, because the natural gas fire boiler CO2 reformer is a 9-10%, coal is a 10 to 14. Oil is 7-9, but the natural gas fire gas turbine is about 3 or 4%. That may cause that larger scrubber in case of the same amount of flue gas treatment. But natural gas fire doesn't have such impurities as SOx or PM or halogens. That will help to improve the solvent life. So that's also need to be considered for another application. Okay, this is it for my presentation. Yeah.
We can do a quick Q&A now, or I can show you the how this connects to what we're doing here.
Maybe we should take a few quick
Let's
breaks.
do that, okay.
Yeah.
Can you give a rough estimate of the cost per ton?
For capture only,
Of
right?
capture?
Yeah.
Capture, yeah. It's really depend on the site condition and
Yeah.
whatever. But so DOE targeted, as you know, about 40 tons per day. I don't know, $40 per ton. Yeah. And we are trying to cross but still higher than that number.
It must be more expensive.
Yeah.
because,
One of the limitations of using amines,
Mhm.
regardless of how proprietary they are, is their ability to be reused. So on the plants you've been running, what is the makeup rate of the amine mixture you have to put back in per 10,000 tons per day or something like that? Because that would affect
Yeah.
performance. Eventually, it comes out in the atmosphere somewhere,
Right,
which
right.
is an issue.
Mhm.
Right. Is that a big number? The loss rate of the amine mixture?
Well, so yeah, basically it's up to the CO2 utilization.
Exactly, right,
Yeah.
right. But I mean, it seems to me that's pretty important to
Yeah.
the ability to do this at the gigaton scale,
Mhm.
right? Because that's what I think a lot of us are very interested in, is
Yeah.
whether it's scalable to the gigaton levels we need per annum to make a difference.
Yeah.
Are
So
you optimistic that?
yeah, so I believe that CO2 solvent capture process is a commercial problem and
yeah.
they're applicable for the large scale, but expensive, right? Yeah.
Right.
So for the larger scale CO2 captures, and always trade off the
Exactly.
cost but we believe that it's technology applicable for all the pre-gas source.
I have a question.
Okay.
During this proprietary process,
Yeah.
Is there any waste or byproduct produced during the process? And if so, what do you do with the waste? What's the process?
Okay. So solvent will be degraded, and then because of some impurities coming out, and then accumulate in the solvent. So sometimes we need to have a reclaiming process to take out the solvent, then vaporize the amine solvent itself by the steam, and
That's the only byproduct that is produced?
then small amount of concentrated, degraded compounds will be discharged from the reclaimer system.
Hope it's
That
small.
will be, hope it's small,
Hope it's
yeah.
small, right.
But it's up to the frequency of the reclaiming process, and also impurity amounts, it's coming from the free gas.
I know the solvent is proprietary, right?
Yeah.
But how toxic is it? Is it toxic? Is it?
Well, amine itself is not
So we're capturing
right.
CO2, but producing something more toxic.
Well, it's being
Well,
reused a lot, right?
yeah,
So
yeah,
it's
yeah.
got some value, you're reusing it, hopefully most of it. That's why I was curious about how much is lost,
Yeah.
because that gets to his point.
So emission itself will be distributed and diffused, but concentrated amount of waste of solvent should be incinerate or some landfill or somewhere. Yeah, we need to treatment for this.
Okay, thank you.
So we can take a couple more questions, and then Tobias is going to speak. Go ahead, please.
Are there any developments for mobile CO2 capture for cars, trucks?
Oh,
To be
this process is not suitable for some mobile system, but probably adsorbent type of the fixed bed type of CO2 capture may be better than this process. Yeah.
So sorry, go ahead.
Yes. Are there any other, like, I don't know if catalyst is the right word, but anything other than amines that, like, you're looking into for carbon capture? Is, like, amines, like, the main?
Yeah, we also doing that development, improve the solvent itself, but also looking at another technology, and so a bunch of the people is working on to develop the adsorbent type and then membrane. So we are always looking at, and what will be the more there's potential to improve from our process.
Okay.
Yeah, and maybe the combinations.
Okay.
So that's a good segue, actually. So from that, give you a quick perspective on how some of those aspects translate into what we're doing in terms of research and development here. So you've seen what this process would look like at the scale of 500 tons a day or 5,000 tons a day.
This will be interesting to see if this works.
Yeah, I don't know. Kevin is operating at 50 grams a day, maybe, so several orders of magnitude below that. But in context of the pipeline on advances and research and discovery that we're doing here, how that translates to Mike.
Oh, okay.
So you actually get 3 talks at the price of 1. I'll only be about, I'll be less than 10 minutes. So I'll give you a quick perspective on what we're doing with regards to integrating the capture with electrochemical CO2 reduction. So this is an emerging project in our group and in part in collaboration with Mitsubishi. So let's see. I have 2 screens and neither of them are working. There we go. So you've seen this slide. It disappears.
Yeah, it's something.
Why don't I skip this guy and just go directly?
Oh, yeah. That should be.
Because I used that one and that one was okay on my computer.
I'll just go directly HDMI. And then what we need is more screens. How about now?
It's in all of them.
I had 10 minutes.
At 10 minutes. Is that what it said?
No, I'll be no. I will shut up at 1:10 because we have to get them to the airport.
You can just tell us.
Just tell us.
I need the process flow diagram though to give you.
Well, you can just.
Yeah, we've got it memorized.
I'll
at this
I'll
point.
sketch it, chalk talk. If it doesn't
Yeah,
work, I'll do
sketch it,
that.
that's right.
There we go.
So you have the flue gas comes into the absorber, right? So this is the absorber, and this is where you're essentially trickling through an amine solution.
Yeah.
So the amine solution, the lean amine. If
Yep.
you're not a chemie, you will be in the next 5 minutes. So this is the lean amine. So this is once the CO2 has been removed. You essentially, imagine this is like a giant shower. You're trickling the amine through here and the flue gas comes out here. So this is CO2 and other products. Depending on where this comes from, on the order of 4% CO2 if it comes from a natural gas turbine. If it's a coal-fired plant, it'll be about 10%. And then this is
Here you are.
clean.
You're good.
Okay.
Sorry, it wanted 2 cords. I don't know
Almost
why.
had some fun with that. Okay, so that's what the process looks like. You've seen this in the previous slide. So this process is well established in the sense that there are commercial facilities available for that. However, still 2 key questions. One is, what do you do with the CO2 once you have it? So you've seen EOR, enhanced oil recovery, in which case the solution is pump it back underground to get more oil out. And in that case, you're geographically locked to locations where that makes sense. So that would be Texas, for example, but wouldn't make sense to do this in New York because people don't do enhanced oil recovery up here. So that's one question is, you can capture the CO2, great, what do you do with it? The other question is, how do you reduce the penalty associated with this? There's quite a bit of steam that you have to generate here to recover the CO2, so there's roughly speaking about 1/4 of a third of the energy that you produce in the first place would go into here to do the CO2 capture. So we're interested in addressing both of those problems. Inspiration number 1 actually came from some work from MIT. So this is in Alan Hatton's group. His idea was, instead of having the amine in a reboiler and using a lot of steam, maybe you can be a bit smarter about how you regenerate the amine, and he has an electrochemical process where essentially you absorb the CO2 just like before, but then instead of heating the heck out of it, you have this electrochemical process where you can replace the CO2 with copper and then send that solution to the cathode where you regenerate the amine. So you can operate this at room temperature, and they demonstrated that you have ultimately not much in terms of energy savings, but it's a completely different approach to doing.
To generate we still have to have electricity.
To doing amine regeneration. So this is inspiration number 1. Inspiration number 2. I should be using the mic. Sorry, I'm loud enough without, right? Occupational hazard. Inspiration number 2. This is from some work that Kevin Kimura did in our lab, which addresses the issue of making something useful with the CO2. So Kevin did some experiments where you're doing electrochemical CO2 reduction. There's a lot of activity in that direction with regards to find a different electrode and operate this under different conditions. But what Kevin found out is that if you actually, instead of setting your potential and then watching what you get, if you switch back and forth and identify different pulsing conditions, you have additional tunable knobs here. So imagine having an instrument like this where you can dial in what you're actually producing. So the input is CO2. The output, you can dial in what you want to produce. If you want to produce methane, if you want to produce carbon monoxide, if you want to produce ethylene, you can control that by adjusting the pulse duration and the pulse potential. The most valuable one in this context would be ethylene. Right? It would be one thing to say, I'm capturing CO2 and I put it in this electrochemical cell, and then I make methane and I burn that again. That cycle would be stupid because you would have a net loss in that process. However, if you can make something like ethylene, that's a value-added product that you can use in established chemical processes. So essentially, imagine having a knob here where you can dial it into ethylene, and just this week demonstrated that you can turn the efficiency of that upwards to about 50% Faraday efficiency. So from a fundamental scientific perspective, it's interesting. From an applied perspective, it's interesting because you can dial in what you're making. Specifically, in an industrial process, you want to dial off the hydrogen evolution. You don't want to generate any hydrogen in this process. You want to suppress that and instead direct the reaction towards the formation of something like ethylene. So those are the 2 key pieces of inspiration. Then the question was, how could you translate something like this to a process that would make sense at larger scale? So this was the genesis of this idea behind the ICER project, Integrated Capture and Electrochemical Reduction. So combine the electrochemically mediated amine regeneration with electrochemical CO2 reduction. Instead of just regenerating the amine and emitting CO2, combine those 2 pieces that I showed you earlier to generate a process that would look essentially something like this. So there's a couple of value propositions to this. One is by operating the electrochemical cell in pulse mode, you can run it for a long time, which is oftentimes an issue with regards to durability for electrochemical processes. So this enhances the stability of the electrode itself. You do all of this in a common amine, so there's cost reduction aspects to that. Value proposition number 3 is interesting because on the anode in this cell, you're generating oxygen, which in most papers about electrochemical CO2 reduction, nobody really talks about what you're making at the anode because oxygen, from the perspective of what you're doing in the lab, isn't really that interesting. But if you think about it at the scale of 1,000 tons a day, if you're making that much oxygen, there could be value to that. And the value in this process is that you take the oxygen generated at the anode, recycle it to the combustion, and create essentially a hybrid oxy-combustion system. Right? So by having an oxygen-enhanced combustion upstream, you reduce the flow rate through here, you reduce the size of the absorber so it has multiplying benefits downstream.
So
and then
how much of the nitrogen how much of the mix between oxygen and air can you get to get rid of this nitrogen?
It depends on what you want to do here. So if it's coal fired, that would be beneficial. If it were gas turbine, turns out you actually don't want to have that much oxygen enhancement. But it's requires still a bit of
Got it,
optimization
okay. Sure.
and process simulation. But it's an interesting
Right
aspect that
direction.
hasn't been addressed yet. So that's the pulsing component.
Interesting.
So current work is then, as far as what we're doing in the lab now, is to understand under what conditions you would actually operate this cell. What would it look like beyond the 5 grams a day to 5,000 tons a day? So what sort of design considerations go into that to make a system that would look similar to what you have in this rendering? The electrode itself, there are aspects comparable to what you have in a gas diffusion electrode. So how do you optimally configure that? Leveraging the resources that we have at Cornell, trying to figure out what's the optimum composition of the electrode. So most of the work to date was just plain copper electrodes, but you can optimize the composition, you can optimize the nanostructuring of it, which specific facet is exposed. There's a lot of upward potential in that direction. And then from a systems perspective, we had a very interesting discussion on this earlier today. A question is not only how do you optimally design this, but what do you produce? So ideally something like ethylene. What's the optimum product that you can convert CO2 into? And then the other question is, when do you produce that? There's an opportunity to develop a hybrid process where you have this classical CO2 capture that you saw in the talk earlier combined with this electrochemical CO2 reduction to create a value-added product, and to do that at times at which you're approaching, if you have, so in this case, if you've taken the energy storage class, you've seen the duck curve, for those of you that have not seen this. But this is essentially, this is the demand curve, and then the orange part is with broader integration of renewables into the grid. What happens is that the baseline power has this suppressed mode here, and the more renewables that you integrate, the further you push this curve down. And it could get to the point where you have negative prices. And negative prices, that would be the prime time at which you would want to turn this system on. So that addresses the issue of when you produce it, and when you produce it, we'll hopefully have some handle on that. So that gives you some perspective on the very early stages of some of these developments. But if you were in a time machine, I don't know, 70 years ago, amine-based capture processes, whenever they were at this stage. So this is, hopefully it doesn't take 70 years to go from here to a deployed technology, but it gives you some flavor for how the work that's happening on campus here is related to ultimately, hopefully, the sort of processes that are operating at scales of 1,000 tons a day, roughly on that scale. So we're still several orders of magnitude below that, but there's a lot of interesting opportunities in this space. So with that, still have a couple minutes for questions, but I'll shut up.
Alrighty, thank you. Something you talked about, so most of your products don't have nitrogen. So
Yeah.
there's no reduction of the amine that occurs electrochemically? It's just a spectator in the electrochemistry and copper?
In our products, this is not yet based in amine-based electrolyte.
Oh, so this
So
is
we
still
don't-
pure CO2?
Yep.
Ah, I see.
So
Well,
that-
pure
that would-
CO2 in aqueous electrolyte,
But
but
that could become an
Okay, so
issue.
that would be-
Might it be a benefit? Who knows?
Yeah, so you'll have some interesting products.
it's on the list as to how does
You need what
Yeah.
knocks down.
how does this pan out if you do it in an amine-based electrolyte? Yeah, that's on the short list.
I mean, there may be some benefits to this in a sense, right? Because you've got some residual nitrogen in the system anyways that's carried through.
Yeah, but I think Linda might be more concerned about degradation of
Yeah,
the amine.
well,
no?
I'm thinking of the
Not
positive side.
necessarily, that the product,
We
so the
could make
selectivity is
ammonia.
gonna be compromised.
Yeah.
Because the reduction potential for the amines are gonna be very similar to
Yeah.
CO2.
Right.
Yeah.
So they'll
Right.
participate in
Yeah.
whatever products you make.
But some nitrogen-based products could be valuable too, right?
Could be, yeah. I mean, the initial assumption is that if we have stability similar to what they have, we would be okay. But that might not be the optimum optimal amine system to work with at a large scale perspective.
Very nice.
Very
Are there other questions?
We should hear more about this in the talks.
Yes,
sometime,
yeah.
right? Don't you think? It'd be great.
All right, if not, you can stay around for the third talk, starting at
15
in 15 minutes. All right, 3 for the price of 1.
So today we don't have a lunch discussion, guys, so sorry, you'll have to buy your own lunch. But, see you